Okay, I'm going to try something. Muito obrigada pela introdução. É realmente prazer estar aqui e gostaria de me juntar a René, dando as boas-vindas aos membros da comunidade acadêmica da UFSC nesta sessão especial. Infelizmente, como vocês podem ver, eu não falo português. Então, o resto da palestra será em inglês. No entanto, se vocês quiserem fazer perguntas em português, meu amigo e colega René gentilmente aceitou traduzi-las.
Muito bom, muito bom.
Obrigada. Ça me fera plaisir aussi de prendre des questions en français. Okay, the rest is in English. Okay. Quantum uncloneability. Welcome, everybody. It's really a pleasure to be here. Okay, in this talk, we're going to talk about ways that we can use quantum information to do really cool things, such as unforgeable money, a type of cryptocurrency using quantum information, perfectly secure communication, unclonable encryption, and we'll talk about also current research and open questions. I'm not assuming any prior knowledge of quantum information, so I'll just discuss the basics that you'll need to understand, but they'll be very, very basic. I'll try to keep this at a very abstract level so that we can appreciate the conceptual contributions, but without going into the details. Okay, so information is physical. If you want to process information, store information, somehow you need to have a physical system that's going to hold that information. If we're talking about conventional computers, what we call in this conference classical computers, one way to store information is, for instance, in the electrical voltage of a circuit. And these states here are discrete. The basic unit is a bit. It's 0 or 1. Okay, either the voltage is on or off, for instance. And this process is described by classical physics, which is the physics of everyday, that you kind of experience in your everyday life. And these physics are really well understood and very intuitive. On the other side, we have what's called the qubit. The qubit is the basic unit of information for quantum computers. And some physical ways to implement the qubit are, for instance, electron spin, photon polarization, etc. And these are governed by the laws of quantum mechanics, which are the laws that we usually talk about, very small things at the atomic scale that are very counterintuitive and don't really follow the intuition that you have for everyday physics. So we use this symbol here to represent a quantum state. It's called a ket. And mathematically, from now on, we can kind of abstract and just talk about the mathematical definition of this. A ket, a qubit, is a norm 1 vector in a 2-dimensional complex inner product space. Okay, so we take the basis states to be this ket 0 and this ket 1. And that means that a qubit is this complex linear combination of ket 0 and ket 1. It's norm 1, so this constraint has to be satisfied. And that's pretty much it. This is the simplest picture of quantum information, by the way. There are more complex ones, but for today, this will be sufficient. Okay, so I want to get right into one of my favorite theorems. It's a really cool theorem. It's simple to state, simple to prove. It has really profound consequences. The quantum no-cloning theorem. Cloning would look something like this. We have one qubit, or maybe a quantum state, if you want to think a little bit more generally. And it would be a process by which, given one input, we can produce 2 identical copies of that input. So in your conventional, classical, everyday life, this happens all the time. We always talk about sending multiple copies of an email, photocopying things, etc. So Why am I talking about no cloning? This is really weird. But indeed, if we're looking for quantum states in a quantum process, there's a theorem that says that this is in general impossible. It's impossible to clone. A little bit more formally, there is no 2-qubit quantum transformation. Okay, I haven't told you about the transformations. All you need to know is that quantum transformations are linear operations. So we can take quantum states and we can apply operators linearly. So the theorem says there are no 2-qubit quantum transformations such that for any single qubit state, if you start with that state plus some workspace and you apply the linear transformation, you would get 2 copies. And I'll go into the proof shortly because it's short proof and you can kind of get an appreciation of the basic concepts of quantum information by looking at that proof. So historically, this is attributed to Wouters and Zurich and also Dijks. But there's this nice quote in this personal recollection of how the quantum no cloning theorem got its name by Asher Perez. And it says, the quote is that, as it often happens in science, these things were well known to those who know things well. And we'll talk a little bit more about, in the future, in the rest of this talk, about people that had the concept or the intuitive concept of no cloning way before 1982. We'll get to that. Okay, so here's what the proof looks like. It's a contradiction. So suppose you did have a U that would clone. Let's start with a generic single qubit state and apply the cloning operation. It's going to make 2 copies and then expand what you would get. This is the tensor product, and that's what mathematically how we can combine single qubit systems to make larger systems. Okay, so you just expand and you get this larger system. Okay, but then you will also clone these basis states, 0 and 1, so we get these 2 equations. And then use these 2 equations and use the linearity that I mentioned to calculate U applied to psi and 0 in a different way using these 2 equations, and then you get this one here. So we've calculated the same thing 2 different ways. We get these 2 expressions, which must be equal, but this is impossible in general. So in particular, if you take these values, 1 over square root 2 for alpha and beta, these two expressions are not the same. So we get a contradiction. So this is a simple version of the no cloning. We can talk about approximate versions, etc., but this will be sufficient to get the intuition for today. Okay, so in general, it's not possible to copy an unknown quantum state. This sounds very annoying. It sounds like it would be a problem if we're trying to do quantum information processing, if we're trying to store data, etc. But where some people see a problem, other ones will see a great possibility. So this is what this talk is about. What cool things can we do with the consequences of this theorem? And one person that noticed, that thought about the possibilities of quantum information for no cloning was Stephen Wiesner. This is an amazing paper. It was written around 1968. Took a long time to publish. It wasn't published until 1983. And there are so many fascinating ideas in this paper. Each time I read it, I find a new passage that I find extraordinary. Okay, so let's start with the abstract. The uncertainty principle imposes restrictions on the capacity of certain types of communication channels. This paper will show that in compensation for this quantum noise, quantum mechanics allows us novel forms of coding without analog in communication channels adequately described by classical physics. So Wiesner is going to tell us that there's some quantum principles. In this case, he kind of intuitively relies on the uncertainty principle that will give us forms of coding that are new and different, that gives us cool things. He has 2 examples of cool things in his paper. The first one is fantastic. It's not part of this talk, but you can ask about it later if you like. We're going to focus on the second talk. The second example It's money that is physically impossible to counterfeit. Okay, so I'd like to tell you about his conjugate coding. And the physical implementation for the quantum information that Wiesner had envisaged are photons, which are particles of light. This laser is actually a beam of particles, a beam of photons. It has millions of photons whenever I turn this on, but in principle it's possible to attenuate this and be sending single photons. A quantum state can be encoded in photon polarization. So we can think about a photon that comes out of this laser as traveling in a direction, which is called polarization. So the photon might be going horizontally. It's kind of like in a wave version, kind of going like this. It might be going vertically like this, diagonally left, diagonally right, like that, or like that. So these are 4 possibilities. The first 2 pair form a basis, and we call that the rectilinear basis, and the second pair will be called the diagonal basis. Abbreviated with this plus and minus. Plus is this superposition. These are called linear combinations, have a fancy name. They're called superpositions. Okay, so this linear combination is plus, this one is minus. Okay, and then the intuition that Wiesner had, and that we're going to rely on for most of this talk, is that if we have a single photon that is polarized according to one of these 4 ways, then if we are the ones who created that polarization, i.e. we know what polarization it was, then it's possible to verify, to confirm that the polarization is correct. And that's done by what's called a measurement. We'll get into that a little bit more into that shortly. But then if we take the point of view of somebody who does not know what the original polarization was. So think about this as an adversary who might not know, who's kind of standing between me and this wall here and does not know how the photon was emitted. And if that adversary tries to create 2 quantum states that have that same polarization, then that intuitively is impossible to do with high probability. Okay, I'm very much a theorist, but I thought it would be fun to try an experiment. Okay, and it has to do with polarizers and lasers. I told you about the laser already. Polarizer is something that's going to block all the photon polarizations except the one that's consistent with the angle of the polarizer. So let's say that if I put it like this, only the horizontal photons get through. The laser sends photons in all possible polarizations. So I don't have enough hands. I need an A, a B, and an E to do this experiment. So 3 people. Does anybody have a first name that starts with A and would like to help? Ow, awesome. So what about a B? Okay, Barbara, yes, and an E. It's tougher. Anybody have a name start with an E? Yes, Eric. Would you like to help? B. Okay, so A, would you please start by choosing polarization? And let's try to use the screen to, okay, could you also hold this, don't have enough hands, and just shine it to the screen? This here, yeah. Okay, so A has chosen a polarization and is shining on the screen. B is going to measure. So say that you know the polarization and you try to detect, to confirm what it is. Okay, so if you put it parallel, the line shines through, which is consistent. A good way to measure is to put it perpendicularly and see that no light goes through. Ooh, okay, and just for fun, just try angles in the between. So we get transmission, it kind of varies, but there's less transmission until we get perpendicular. Okay, let's go back to perpendicular. So this would be the somebody preparing and verifying. But E does not know the polarization, and we'll try to possibly measure it and gain some information about the measurement. Okay, so if he guesses correctly the polarization, he will not interfere, i.e. if it's vertical. Okay, but any other angle will let some light through, and that's what can be detected, and that's the method that can be used to check if there's interference in the system. Does anybody have any questions? Oh, can you see well enough? Okay, thank you. Okay, so let's, oh, nice, very nice. Okay, then if B goes perpendicular, that would be the way to confirm that the polarization is correct. And then if we have E in the middle, if E guesses correctly, then there's no interference, it's not detected, but any other angle of the polarization in the middle will transmit some light, and that's what can be detected on the B side. Okay. Okay, thank you very much. Okay, so what we just saw, attempts to gain information about the polarization unavoidably disturb the polarization. And as a little token of appreciation, literally a token, there's this game. It's a board game. It's called Q-Turn. Unfortunately, it's out of production, but the authors have generously made it available online. So I've printed some copies for our A, B, and E. Thank you very much. Okay, so this is how Wiesner envisaged the quantum banknote. It would be, well, a device that would store these polarized photons according to some secret known only by the bank. Point being that the bank, knowing the secret, could verify, as we just saw, the polarization, but that anybody trying to read off the polarization would unavoidably be detectable. Of course, Wiesner was very much aware that this was technologically very difficult, borderline impossible, because it's very difficult to store a quantum information, for instance, photons, for any period of time longer than nanoseconds. And this is still true today. So I don't necessarily recommend investing into quantum money. That tends to decay here very quickly, very, very quickly, talking about deflation. Okay, the security of Wiesner's quantum money scheme. Formally, we can ask, what's the probability, what's the chance that an attack here would be able to take one piece of quantum money and produce two identical pieces of quantum money? Very similar to the picture of the no cloning, but this is the more precise question in terms of these polarizations. So how does the difficulty of cloning quantum money scale with the number of qubits n? Wiesner already had a security argument. It's not a full proof. It's not perfect, but for 1968, this is really amazing. Okay, so he says, could there be some way of duplicating the money without learning the sequence n? No, because if one copy can be made so that there are two pieces of the money, then many copies can be made by making copies of copies. Now, given an unlimited supply of systems in the same state, that state can be determined. Thus, the sequence n could be recovered, but this is impossible. So he already had an intuitive notion of no cloning, maybe uncertainty, etc. But really he was thinking, well, if you can make one copy, you can make multiple copies, you can learn the entire sequence, but that should be impossible. Okay, maybe it's a little bit circular. We can forgive him. Sounds a lot like no cloning. Remember, this was in 1968. This was before the word qubit existed. This was before the formal statement of no cloning was given. This is the first quantum cryptography paper ever. It took, I think, 45 years to get a formal proof of what would be the best success probability in terms of n. This was done by Molina, Vidic, and Watrous. And it's a nice solution. The answer is 3/4 to the n, which means that if we can increase n polynomially, the security goes down exponentially. So this is fantastic. The proof techniques that they use are semi-definite programming. We've heard a little bit about that this week. So very nice techniques to mathematical techniques with a nice application here to quantum information cryptography. In the last few years, there's been a revival of interest in quantum money, and lots of new questions have come up. So for instance, Gavinsky had a scheme for quantum money with classical verification. So would it be possible to send out quantum states such that the communication in order to verify the quantum states will only have to be classical? So he showed some schemes to do this. And another important question was described in terms of public key quantum money. And this question is it possible for anybody to verify the money? This makes things a lot more useful. So in Wiesner's scheme, only the bank can confirm that the money is authentic. So good luck trying to go to a merchant and to spend the money, because they can't tell whether the money is valid or not. Public key quantum money would allow anybody to verify it, but would still have this uncloneability property. Let's say that, let's summarize this by saying that we know this is interesting. There are some schemes that have been proposed, but it's still very much ongoing work to find new and practical schemes for public key quantum money. Okay, so I'd like to go into another use of conjugate coding, and likely many of you have heard about this before. This is when conjugate coding really became well known and popular. So the story starts in 1979. We have Gilles Brassard, had just completed his PhD and was a very young professor at Université de Montréal in Canada. And we have Charles Bennett, a physicist at IBM in the US. And true story is that Gilles was swimming in the ocean in Puerto Rico, minding his own business, and then Charles Bennett swims up to him, complete stranger, and starts telling him about the way that he knows how to create unforgeable quantum money. So Brassard was very surprised, but he found the idea very interesting. And by the time they had swam back to shore, they had already had ideas of how to improve Wiesner's ideas. It took a few more years to perfect the idea, but this eventually became what's known as BB84. To complete the story, I should say that Charles Bennett was an acquaintance of Stephen Wiesner, and so Charles Bennett had knowledge of the manuscript that Wiesner had written in 1968, and had been trying to bring this idea to cryptographers in order to make it more complete and find some great applications. And I dare say that in this case, this was a very successful collaboration, and still to this day, Bennett and Brassard are very close collaborators. They recently were awarded a Wolf Prize. Okay, so quantum key distribution solves the following problem. It's the problem of secret communication. Here's a conversation between Alice and Bob, and it's not really encrypted. You can kind of guess what's going on. And if there's an eavesdropper on the line here trying to listen, then Eve will be able to tell what's the conversation, right? So what if Alice and Bob are trying to, thanks, I don't have enough hands. What if Alice and Bob were trying to keep privacy? So an encryption scheme would render the communication in a way that Eve would not be able to understand anymore what's going on, but Alice and Bob can still communicate. Okay, so the ultimate goal that we want to talk about today is unconditional security. Often quantum information allows us these higher levels of security. And by that, I mean, well, there are all these schemes that are widely used over the internet, etc., such as the Advanced Encryption Standard, AES, that uses, that based on the difficulty of some computational problems. So what we do is that we assume that computers are really not that good. That means, and that implies security for the schemes. Okay, another one is RSA. It does public key cryptography, and the security of RSA is based on the difficulty of factoring. So in principle, it's possible to break these schemes. Okay, so when you see the little lock on your on your browser. It's because you're using this, but this is not unconditionally secure. There is an encryption scheme that is unconditionally secure. It's called the one-time pad. And the method to encrypt using the one-time pad is very simple. If we have a single bit that we want to encrypt, what we do is we generate one key, which is a random bit. And the ciphertext is this combination. This is the modular 2 addition, or the XOR, of the plaintext and the key. And then the point is that this ciphertext will be uniformly random. As long as the key is random, and as long as the key is only used once, then we have this random property of the ciphertext. So therefore, the plaintext will be perfectly concealed. This is called the one-time pad because it's very important that it should be used only once. It's very easy to show that if you reuse the key to encrypt 2 different messages, then there's some information that will be leaked. The one-time pad key is not very practical, and I'll show you one of the reasons shortly, but it has been used for very important communication systems. For instance, the Washington-Moscow hotline used the one-time pad key encryption scheme, and the problem with this is that we need very long keys. You need a key that's as long as the message, and it's kind of throwaway. Once you use it, you need some new keys. So the keys that were used in the system had to be somewhat shared between Moscow and Washington, and this had to be done in a secure way. I think they were sending diplomats back and forth, actually, with briefcases full of keys. Okay, so you need a long key, but it's very secure. There's another problem. If we're talking about a network of communication, then there's many users. We have 2 users, 1 secret key. 4 users may want to talk different ways together. There's 6 ways that 4 users can talk. So these keys should be specific for each pair of users. So we need 6 secret keys in this case. 8 users, 28 keys, etc. So it grows quadratically in the number of users. So that's a problem. Not only the idea of sharing long secrets, but also the idea of how many keys you'd have to have based on the network that you're using. Quantum key distribution comes to the rescue and solves this problem in a very elegant way using quantum communication. And again, it's based on the intuition of the no-cloning theorem, namely that the person who sent the photons can verify them, but an eavesdropper will unavoidably introduce noise. Okay, so Alice will send polarized photons, Bob will receive them, and an eavesdropper here does not know the original basis. Okay, so eavesdropping implies errors, implies detection. So the idea is that we will use a quantum channel to send a random key. At this point, the key is not very precious at all. It's not the message. It's a random key. And if our process works and we're happy with it, we'll confirm that the key is going to be, that the key is indeed secret. It's secret against Eve, and we'll use that key as in the one-time pad system. There's a chance that Eve will interfere and will decide that the key is not secret. But then we can just throw it away and start again. We haven't risked anything at all, other than maybe time to communicate. Okay, so here's a sketch of what a run of this protocol might look like. We have Alice that chooses an encoding basis. So this is a random choice, as you can see. Okay, and then she chooses a random bit values, and then encodes each bit into the given basis. So, for instance, 1 will be encoded as vertical, 1 in the diagonal basis will be encoded as left, 0 in the diagonal basis will be encoded as right, etc. And she sends those polarized photons or qubits to Bob. Bob doesn't know the basis, because that would, So what he does is that he chooses a random basis for his decoding. This is a random choice here. And he measures the arrived photons in the basis that's given. And the point is that, as in the experiment that we had previously with the polarizers, if he chooses the same basis as Alice, he'll measure the same bit value. If he chooses a different basis, then there's no guarantee. So by classical communication, Bob can tell Alice what was his basis choice, and then they can simply throw out the runs where their bases did not coincide. That's by the public discussion, and the guarantee is that with no Eve and perfect experimental conditions, no noise whatsoever, they will have the same bit string here at the end of this round. Okay, and this is indeed confirmed. Now, if there's an Eve in the middle, we'll take the simplest possible picture. This is not the most general way that Eve could be acting, but let's say that Eve in the middle decides on a basis to measure in. And Eve does not know this choice, and she does not know this choice. So what she can do is that she'll measure in a random choice of bases. The point is that when they do the public discussion, Alice and Bob will notice, well, with some probability, will notice Eve's intervention. Namely, when they chose the same basis, Alice and Bob's bases coincide, but Eve's does not. There's a chance that, look here, Alice sent a 0, but Bob measured a 1. So here, her interference will be detected. And then there are mathematical techniques to decide if there's enough privacy in this communication in order to amplify it and to create a shared secret key, or maybe there's too much noise and we'll say that Eve has indeed completely gained too much knowledge about this shared secret, and Alice and Bob can just start over in that case. So in talks like a public lecture, a person might say, well, the security of BBD4 is based on the no-cloning theorem. It's not totally false. The no-cloning theorem definitely plays a role. If we had quantum cloning, if cloning was always possible, then Eve could simply clone and she could learn information, and there'd be no way that quantum key distribution could work. However, the actual security proofs, and even the definitions, took quite a while to appear, let's say, in the literature. This was an open problem for at least 15 years to have actual security proofs for quantum key distribution. And they led to very elegant techniques, including quantum error correction, entropic uncertainty relations, and much, much more techniques that were developed in the literature. You may be wondering if quantum key distribution is something practical today, and the answer is a resounding yes. Quantum key distribution does not require a full quantum computer. It's something that can be done with very simple technology. So we had experiments starting in the late 80s, proofs that I already mentioned, bank transfers, networks of QKD. Now we have satellite to ground QKD. We have QKD commercial products that are available for purchase. Plug and play into your network. So this is in contrast, by the way, with quantum computers, which are still in their infancy in terms of being developed, because quantum computers are much more sophisticated in terms of their quantum information processing power. Okay, so maybe are there any questions about quantum key distribution?
It's actually a kind of meta picture. I really like that picture of the money with the pyramid and the eye that looks like Sauron. Do you know who made it?
The picture of the money, the green money bill? Yeah. This is available in too many clicks, but the green money bill is in I think Science, where they wrote some sort of kind of popular account or accessible account for quantum money. It had like copyright AAAS when I projected it. Okay. So what else could be made unclonable? What other cool things could be made unclonable? I think this is the tip of the iceberg. I think we kind of have these nice applications, quantum money, quantum key distribution, but there is so much more to be discovered. And actually in cryptography and conventional, or say modern cryptography, one of the things that we look for are building blocks. So we want some small units of information processing that can be combined in very astute ways in order to create larger functionalities. So for instance, if you're familiar with things like oblivious transfer, it can be combined with bit commitment to get like all of multi-party computation. That was just a side comment, but it's kind of motivating, I think, this entire area of research to try to get more unclonable functionalities. Okay, one of them is unclonable encryption, and I think this is a underappreciated paper, 2004, Gottesman. 2004 was just right about the same time that we had the first proofs of security for quantum key distribution. We were starting to understand mathematically what these things represented, and he came up with something called unclonable encryption. Okay, this picture is, let me take a few minutes to explain it. This explains what we're trying to do in unclonable encryption. We have a message. Think about it as a randomly chosen bit string, n bits. Encryption means we're going to have an encryption scheme. We're going to have a way, using a key, to encode a message. So this is this enc thing. So this says, encrypt the message M using the key K. It's going to be a quantum encryption. So the output of the encryption will be a quantum state. Okay, this is not just a qubit. It could be a multi-qubit quantum state. And the key will be a random bit string of length that's proportional to n and some security parameter kappa. Okay, and then we'll send this encryption, this encoded message to an attacker. We'll send it to Eve. And then Eve is allowed to apply any quantum map, and she tries to split it. So she splits it into two. One part goes to Bob, and she keeps the other part. Okay, kind of imagine that Eve is both here and here. And next, Bob and Eve get the key. So they both know the encryption key, right? So initially, if you had the encryption key and you had the ciphertext, you can decrypt. That's the usual correctness property. So both Bob and Eve get the key. And then Bob, think about Bob as being honest. Bob is going to do some process that will either accept, that's what ACC means, and output a bit string, M prime, or he might reject. And then Eve does some process, some arbitrary process, and outputs a bit string ME. And for security, we're going to ask that the probability that Bob says accept, so he's okay, he says, yeah, I accept, and Eve is able to output M. So she's able to predict what the original plain text was. So we want that probability is small. So it's almost equal to the probability that you could guess M correctly, 1 over 2 to the n, 1 over 2 to the n. Okay, so to double check our intuition about this definition, notice that if this was the classical encoding, so say we had just a regular classical encryption scheme with classical messages. So a classical attack could simply copy the message, send one copy to Bob and one copy to Eve. Then when they have the key, they can both decrypt. Okay, so this would make no sense to talk about this, and classically it would simply be probability 1. So unclonable encryption is not only about achieving better some known scheme, it's about a new scheme that you would never even think about if you were just thinking about conventional or classical information. So quite amazingly, Gottesman showed, oh yeah, there's also this correctness. By the way, this is not his exact definition. This is, for the purposes of this talk, I thought this was easier to digest. So also correctness, okay, if there's no attack, Bob should output accept and M. Okay, the point being that intuitively, if Bob accepts, he has the correct string, he's able to decrypt, and M prime is equal to M. If he rejects, then we'll say that Eve might have a high chance of decrypting, so it's kind of like the case where Eve might have the plain text, maybe we should not continue the protocol, etc. Okay, so quite amazingly, already in 2004, Gottesman had an encoding scheme for unclonable encryption. And it was inspired by quantum key distribution and also some other topic that was kind of hot at that time, which was quantum message authentication. However, he admits in the conclusion that really maybe what he's doing is really maybe not exactly unclonable encryption. And indeed, if you look about it and with hindsight, maybe his encryption was more like tamper-evident encryption, that we would be able to detect if Eve has possibly stolen the plaintext, but we can't really prevent it. Okay, so I have not, okay, I'll skip this. Basically, I just summarized it, that there could be some maybe stronger possible unclonable encryption scheme. And indeed, this is ongoing work with a master student of mine, Sébastien Lord. Strong unclonable encryption has this symmetry. Now we're talking about two possible receivers, Bob 1 and Bob 2. We still have a message, a quantum method to encode the message, an attack. And then Bob 1 and Bob 2 both get the key. And then they both need to output a bit string. And the point is that we want to say that no matter what attack is done here, it's very difficult, or i.e. they might as well just both guess, for both of them to be able to output the message M. So this has like built-in unclonability. There's no concept of detecting or not detecting. It's simply impossible for an attack to split a ciphertext into two such that once the key is received, both receivers are able to decrypt. Right now, we don't exactly have, we have a scheme, but where the proof does not exactly satisfy this. So there's a little 9 in here. A big 9 some days I think about it, but anyways. But still, if you go to bigger messages, we still get something that's better than classical encoding. Classically, of course, this still makes no sense, and you would always be able to have 1 here. So if you scale it up a bit, you still get something that's smaller than 1, and so you're still able to see this quantum effect. Other unclonable type of functionalities that have been brought up in the literature is quantum copy protection. So this one is by Aronson in 2011. And this was the first paper to ask about unclonability of programs. So far, we've talked about unclonability of information. Actually, it's a bit of a hierarchy. So initially, you have unclonability of a quantum bill. A quantum money does not have any information in it. It's an unclonable thing, a token, a device, or something. And then we had unclonable encryption, which is to store information in an unclonable format. And clonable programs store functionalities, so things that you can run. Functionality is something you can give it input and you get an output. Okay, so Aronson was asking about copy protecting programs. For instance, for the simplest case, here's one that's maybe the easiest to understand. Consider a point function. A point function is a function that is 0 everywhere, but there's a single point, a. When x is equal to a, f of a is 1. So think about it maybe like a password verification program. So there's a single input that we'll accept. Then if you're talking about copy protecting, you would like to distribute a quantum state, let's say psi a. So somehow the quantum state encodes this special point a, such that anybody with psi a can evaluate f of x. So you can indeed, if you have a and psi a, you can kind of combine the two together to the output, and the output will be 1. And you can also compute the function on any other point. But somehow you would want that if you take psi a, which is the program, you give it to an adversary, and the adversary splits the program into 2, then it would not be possible for both Bob 1 and Bob 2 to simultaneously be good at evaluating f. This is very hand-wavy, and actually I'm not aware of anybody that's formally defined this, and they're this is an open question if there would be a way to do this. Aronson did have some results in his paper towards achieving unclonable or copy-protected functions. But as all great complexity theorists know, the initial results were in the oracle model. So if you assume a trusted device, i.e. an oracle, then we're able to have copy protection for all programs. And what the trusted device does, it kind of acts like a gatekeeper. So we're going to have a random quantum state that is used as a gatekeeper. And if this state is given as input to the oracle, then the oracle is going to evaluate the function correctly. And here we're therefore using the unclonability of the quantum state, like maybe think about it as a quantum money or a quantum token. You put that into the trusted device, which is going to compute the function for you only if that input was intact. And then you can use the quantum no cloning, et cetera, to kind of guarantee that only one instance of this program can ever be run at one point in time. At a single point in time. But this is somewhat unsatisfactory because pretty much all of the work is offloaded to the oracle. So we're just using the unclonability of the token and not really the unclonability of the program itself. So really it's a wide open question, copy protection for any non-trivial family of functions without an oracle. Okay, so I'm already at the summary, and we've shown that unclonability is a non-classical phenomena that can be used to our advantage in cryptography. And this complements a lot of the topics that we've been discussing this week. We talked about non-classicality in terms of correlations, non-locality, et cetera. But this is another non-classical phenomena, the no cloning. And it also gives us some really interesting applications. I have an entire thank you slide. It's kind of out of the ordinary to have so many thank yous, but really I wanted to, and there's actually 4 points. I want to thank the Q-Turn team, and so, I mean, including the local organizers, the non-local organizers, the program committee chairs. I think like when we say organizers, that's like a big umbrella for all these people. The attendees too, the presenters. Our sponsors, without them, be very difficult for me and my research group to be doing this work. It's kind of common to thank our ONE's research group. This is the Ottawa Quantum Information Group. But also for the context of QCrypt, I want to acknowledge those who support me outside of the academic environment. So my wonderful family, they're super supportive of my work. Thank you very much.
So we have plenty of time for questions. Perguntas em português também são bem-vindas. Posso traduzi-las.
Hello. I will try asking in English. So basically, when you try to send a message for the other, message, the attack, you always assume that I am trying to read what is encrypted. So, but if I try to erase what's encrypted, so how this happened of the code? And I will have another is how many energy I need to expend to make some cryptography. So for generate this code.
Okay, so 2 questions. Was the first one addressing this type of picture? So in Eve here, who's in the middle, I think I mentioned this was a simple type of attack, and these were the first attacks that people really considered when they were talking about QKD and trying to imagine how maybe security could be proven. To this day, it's still very misleading because really the security proofs, they're against all possible attacks. So this is maybe like a cartoon version. So erasing a qubit, good point. So maybe she just tries to take one, steal one, and then wait until later, until there's the communication, and take advantage of the qubit that she's kept to gain some information. So this can be modeled, any type of interference can be modeled as a quantum channel. So the security proofs don't make any assumptions about the quantum channel that are applied. Well, the current modern security proofs, initial versions did have some assumptions, and we still see today, like intercept resend, which is kind of this, optimal cloning, etc. But the most general security proofs make no assumptions on what Eve is doing. In particular, maybe Eve could like do some attack that combines all these qubits, right, that are sent in some very smartly chosen basis. So that needs to be also covered by the formal security proof. The other question is, and they are in current versions, the other questions about energy use. I don't know what to say. That's like, are you concerned about the cost to the environment, or yeah. I don't know what to say. Does anybody have an idea of energy use in QQD? To produce a qubit. Yeah, well, this is 10 to the 6 qubits or something. But they're not really useful because there's too many. So I know that one of the difficulties is like creating single qubits, and that takes time, and yeah, it does take energy. I don't know if on a large scale and planetary scale, maybe this is too expensive, and maybe that's something that we need to work on. I don't know.
I heard of Landau's principle, which talks about the cost of erasing a qubit. Could be that related to the question? Maybe? Does anybody know? They say it depends on the temperature, but well.
Well, so I've seen a few of the commercially available machines, and they're pretty normal machines actually. They fit on a desktop, they plug into the wall, so they use roughly as much power as a household appliance. They're sort of normal. You know.
Good answer. Any other questions?
Hello. So I have a question about the unclonable encryption that I didn't fully understand the setups. So is it that the key is public, so everyone has access to it? And the encoding is which type of things? It's like a unitary quantum one-type pad, or?
Okay, yeah. Good. I'm glad. Okay, I'm glad I can explain this a little bit more. So the key is revealed in the second phase. Okay, so the attacker does not have a key. If the attacker had the key, the attacker could decrypt and there'd be really nothing to talk about. Okay, so the attacker does not have the key, but the point is that both Bob and Eve will be able to get the key when they have to output this accept and this string M. Okay, so just as a sanity check, if this is classical, again, the attack would be able to make 2 copies. Given the key, they could both decrypt, and then Eve could always output M. And in that case, we don't even care what Bob would do. Okay, and then the second question is about the encryption, or the encoding, as I called it. You want to know a little bit more about the encoding? Yeah. Okay, so abstractly, it's a way to transform the bit string M into a quantum state. So one encoding that you could use would be conjugate coding. Would probably be a good idea. The first thing to try would be to choose a random basis. Maybe K could be the random basis, and then you would encode the bit string M into the random basis, just as in quantum money or QKD. That would give you as output a quantum state. So it's a unitary controlled on the key K, if you like.
Thanks.
Still plenty of time for questions.
Thanks for the talk. So actually, I'll kind of remembering Glaucia's talk, we saw that these device-independent quantum cryptographic schemes, they are kind of far away somehow, right? I mean, the bit rate is still quite low. So I'm wondering, like, these machines which are kind of being sold, I mean, are they actually of any use, or is more like still kind of a proof of concept realm?
Oh, okay. Yeah, excellent question. Let me just actually, Glaucia, this is a isometry, because it might actually expand the space, so it's maybe not a unitary. Okay, so the commercial QKD products are secure if you are able to apply these security proofs. And to apply these security proofs, you need to be confident that your system acts according to the hypotheses of the security proofs. And the security proofs assume, for instance, trusted measurements, so that when you have a measurement device and you read a measurement outcome, then it was indeed the quantum process that was underlying that device. So if you're happy to assume that, and maybe it's reasonable, maybe like I have, maybe, I don't know, Renee is super multi-talented and is able to build his own system, trusts all the components, and then he has one at home, and then he has another one at the office that he also built, then he has this fiber optic line between the two. And the point is that he doesn't trust the fiber optic line, and that's what the security proofs say, that you can actually end up detecting the EVE on that line. But if you're okay with your local labs, then you can use these, and the proofs are applicable, right? What Glaucia was talking about was, what if you don't trust the device that you've built? And that becomes much more technologically challenging, and also theoretically interesting.
Sorry, can I continue? So then, aren't we then the same page as the classical products that we have? I mean, like, we also have to assume something about the classical security proofs, right? I mean, we are always assuming something in a sense.
Oh, okay. So then you're saying, well, maybe we're trading a computational assumption, which is what we do for conventional public key cryptography, for an assumption on the device. Yeah, that's one way to see it. But I think it's a very different type of assumption, and classically we don't even talk about trusting the processor, but you do also trust the processor, right? That's almost implicit.
Questions?
So what was the other application that Wiesner said?
Oh, awesome. Okay. Wiesner had two examples, as I mentioned, and we only talked about example one. Okay, blah, blah, blah. We only talked about example two. Example one, just as astounding, okay? So in his words, it's a means for transmitting two messages, either but not both of which may be received. Okay, so he was conceptually talking about a way to encode two messages, let's say x0 and x1, send that to Bob, and then Bob would be able to receive one of them but not both of them. It sounds, again, useless. Why would you ever want to send two messages, but only one arrives? But cryptographically, if you can prove that provably only one of the two messages arrives, that is super powerful, okay? And nowadays, we call this oblivious transfer. Conceptually, we talk about Alice inputting 2 bits, and Bob can choose 1 bit. He'll get BC, C is 0 or 1. The point being that the other bit is completely lost. He'll never be able to see it. And, okay, actually Wiesner says, okay, this is a way to do it, but then he actually says, oh, it's actually not going to work. So he doesn't actually show how to do it, which is a good thing because this is also impossible quantumly. But the idea that he kind of conceptualized this primitive is really interesting because it was reinvented in 13 years later by a cryptographer called Rabin. And then in cryptography, it became super important as a building block, as I mentioned already, for all of cryptography. So somehow this, this paper of Wiesner had these two really groundbreaking ideas that are really important in cryptography. Yeah, so oblivious transfer, called OT. It's a building block in cryptography. It's important, and complex problems such as multi-party computation can be based on the existence of this thing.
Sorry, but then what's the difference from random access codes?
The security definition for random access codes is different. So random access codes, one way to do it would be to actually, oh, that's private information retrieval, sorry. Access codes. In that, we ask to encode lots of information into a smaller state such that it's possible to extract one part of information. But we don't really want, if I'm not mistaken, we don't really have a cryptographic definition that says that it's impossible to get the other bits of information. It's about the efficiency of encoding that we're interested in random access codes, but we don't have the full cryptographic requirements here that we need for OT in order to make it into a building block.
Thank you.
So, hi. So I didn't understand. Is oblivious transfer impossible to be achieved as well?
Yeah, oblivious transfer is impossible in the plain model for classical information or quantum information. And what we do, if I said that it's a building block, you're like, okay, what are you talking about? But what we do is that we add some assumptions. So you could just say, oh, I'll assume that this primitive exists, and then what can we build? So that's like, okay, I assume this exists, and then what else can you do? Or then you can also go and implement it with your favorite assumption. So you can implement it with a computational assumption, implement it with bounded storage, or other things, and then you still get the entire, all the cool stuff still, well, hopefully still works if you've done your proofs correctly, but then you can kind of just study that small building block and how to build it.
And a second question then, do you see any connection with of oblivious transfer with some compatibility notion, as if you cannot read both of them at once and you need to choose one of them? So do you think it might have some connection with other notions of compatibility in quantum
Yeah,
theory?
is it like compatibility of like quantum measurements? Yeah, this has been exploited in things like achieving oblivious transfer in the quantum bounded storage model. So like there are methods, if you add some extra assumptions like noisy storage, bounded storage, that you can take advantage of conjugate coding, like maybe encoding each bit in different bases, and then it's not possible to make a single measurement that would extract all of the information of both bits, and then maybe you can amplify that, or maybe you could, yeah, such techniques have been looked at, definitely.
Okay, thank you.
Yeah, just a quick question. There's this notion of zero knowledge proving, and I was just wondering, I mean, maybe I get it all wrong, but can you apply these no copy theorems to help you come up with, zero knowledge schemes in a kind of quantum setting?
Yeah. Zero knowledge would be another talk. So super interesting. Zero knowledge is like, for those who don't know, it's like a way to prove something to, maybe Alice can prove something to Bob so that Bob becomes convinced but doesn't learn anything about the proof. That's an excellent question. So I think there may be links between zero knowledge and unclonability. Like, for instance, maybe zero knowledge unclonable proofs would be like two different things coming together. That might be possible and something interesting to look at.
So the connection I had in mind was, say Alice comes with psi, and Bob is meant to apply these unitaries and prove something, but since we know that Bob doesn't know psi, he couldn't just sort of set a copy aside and sort of exploit it to gain information and then kind of process the first copy and hand it back as if nothing happened. So, Alice knows that Bob couldn't have extracted information by virtue of his not knowing psi initially.
yeah, maybe we could take advantage of that.
Maybe one last question. If not, I have one, and then 3 announcements. So I have a naive question. If I remember correctly, you told us about ESA and RSA, right, as classical cryptography protocols that are breakable in principle, but they're very difficult to break. So is there any classical protocol that is in principle unbreakable?
Yeah, so it's usually a trade-off between efficiency and levels of security. So the one-time pad is unbreakable. The trade-off is that you need really long keys. Okay, RSA AES is breakable in principle, but the advantage is in the short shared secret or the public key cryptography that's not available for unbreakable crypto. Yeah, typically you can get anything unconditional if you're willing to pay for it. The premise of QKD is that we're not willing to go through the extra work of sharing these long secrets by diplomatic briefcase.
Okay, thank you. So let's thank again and for this really nice presentation.